Okay, so we've got a particle of mass 0.4 kilograms rests on a horizontal surface. So we've got that's 0.4 g. It's on a surface, so there'll be normal contact force R. Coefficient of friction, so I'll put down mu equals 0.2. So a force of magnitude 1.2 newtons acting at an angle of theta degrees by the horizontal. Okay, I've got lots of different chances of theta, so I'm going to need a diagram, separate diagram for each one. The first one, theta is at 0, so that means it's being pulled there with 1.2 newtons. And obviously, we've got friction coming back there because it's going to oppose motion or desired motion. So, I've defined friction, I know what mu is, so I'm going to have to resolve vertically to find out what R is. We've got a limiting friction, so resolve vertically. No acceleration there. I'm just going to say that up equals down. That means that R equals 0.4 g. That's good. I've got limiting friction, and that will say that will be equal to mu R. So that will equal 0.2 times by 0.4 g, and that equals 0.784. And now I can resolve to the right, and I'm going to have to say the resultant force equals the mass times acceleration. What have I got going to the right? Well, I've obviously got the 1.2, nothing else going there, but I've got the minus F, so it's minus, I've just worked it out, 0.784 equals the mass, which is 0.4 times by A, and that gives me that A equals 1.04 meters per second squared. And now I've got the second one, part 2. I've still got the same particle resting on a horizontal surface, and put the forces in. So I've got the weight straight down from the centre of mass. So weight still 0.4 g. R goes straight up from the surface. It's now been pulled at when theta is 20 degrees. It's probably a bit steep, but 1.2 newtons, and that is 20 degrees. And friction obviously opposes motion or desired motion. And so we've got to do pretty much exactly the same thing again. I've got to resolve upwards. A little bit more careful now because I've got this component here. If I split that into its components, I've got this component here and this one there, and it's this bit which is the up component. And so I get, obviously I've got the whole of R, plus that'll be 1.2 sine 20, and that's going to equal 0.4 g. And so R will equal 3.50957. F lim, limiting friction, that equals mu R, otherwise F is less than or equal to mu R, and that will equal mu 0.2 times by 3.50957, and that equals 0.7019. And now we can resolve to the right. So resolving right ways, resultant force equals mass times acceleration, which is, I've got this force here, which is 1.2 cos 20. So 1.2 cos 20 minus my F, just worked it out, 0.7019 equals the mass, which is still 0.4 times by the acceleration, and that will give me that A equals 1.0628. So round to 3 significant figures as well. Part 3, same thing again. I've now got 70 degrees. Draw the object and put the forces on. Good weight, always put the weight on first, 0.4 g. Normal contact force, R. It's much steeper, this 1.2. And obviously friction opposes motion or desired motion. This is likely to be different to what's happened before, or else they're just asking us the same question again. So what am I going to do? I still will resolve vertically, and that will say that R plus, split my force up if I need to, like so. That's so, and that bit is 70 degrees now, isn't it? Yep. And so R plus 1.2 and it's going to be this bit here, sine 70 equals 0.4 g, and so r equals 2.79236. We've got f lim, and that will be equals mu r, which equals 0.2 times this, which equals 0.55847. Resolve to the right, resultant force equals mass times acceleration, and that will be 1.2, and then it's going to be cos 70 minus what I've just worked out, 0.55847 equals 0.4a, and this bit here actually only comes to 0.4104, and that's the friction. That's not enough to beat the maximum friction. This actually gives a negative acceleration, which will be saying that if I put my acceleration on here, probably should have had it, that means it's actually going the other way. Well, that's rubbish, it can't happen. So here a equals 0 because friction won't be overcome. And finally, part 4, I'm going to do it in red because it's going to get a bit squished here. 4, I'll draw the picture as usual. We're like so, and we've got the weight coming straight down there, which is 0.4 g. Got normal contact force going up. We've got 1.2 going straight up. Therefore, there's no friction because there's no forces going horizontally, no friction, and I need to see it might take off. So I just need to work out what we've got, and 0.4 g is that equals 3.92, and so therefore it's not going to be accelerating upwards. If the force which was applied to it was bigger than 3.92, so if this force was 5, then it would be accelerating upwards, but it's not. That's 3.92. It's only got 1.2 up there, therefore a particle won't move, and therefore acceleration equals 0 for this one as well. And that's question 5 done.